Hello everyone, my name is Robert and this is Lab 5. So this video I decided to look at a HowRidiculous video of them dropping a 10 kilogram bowling ball off a 165 meter dam in Switzerland, and they're going to drop it onto a trampoline, and I wanted to see what was the final velocity of the bowling ball. So for this I used the model using snippets of their video as well as crafting a computational model to estimate its final velocity. Results of this, I did find the ball to be falling around 61 meters per second or 130 miles per hour. So fundamental principles for this lab, we use the momentum principle from Newton's second law, namely the velocity update equation and position update. And then for the second part, where I wanted to estimate the spring constant of the trampoline, I use the energy principle instead. For the momentum principle, I am going to be using the force of gravity and accounting for drag coefficient through the air. So looking for the final velocity of the ball, my system is the bowling ball, surrounding is the earth. I have the height of the dam, which is given in the video, as well as the mass of the bowling ball, which is the only bowling ball that is stated to be 10 pounds or 4.53 kilograms. I had to estimate the time of the drop using a continuous shot from the video. Velocity initial, you can see he's holding it at steady position, and we're looking for final velocity. So to estimate the final velocity, I simply found a continuous shot in the video of where they didn't use any jump cuts, and seeing the ball fall from his hands all the way to the ground, 165 meters. I calculated this to be 360 frames until it actually hit the ground. We see the dirt splatter, not the sound, and that came out to be 6 seconds. And then using the velocity update equation, I found it to be estimating around 58.86 meters per second, only accounting for gravity and not drag. So to account for drag, I built a computation model using from Lab 2. For this, I used the total net force to be the force of gravity minus the force of drag as it's falling. The total drag equation is 1/2 density velocity squared coefficient of drag times the cross-sectional area. I found these values from the internet of the density of air to be 1.293. The velocity will change as it's moving or it's speeding up due to the acceleration of gravity. The coefficient of drag for a sphere is 0.47. In the cross-sectional area of a bowling ball that weighs 10 pounds, I found pi r squared, which would be 0.0366. Using that, I used the same code from Lab 2 to calculate it, the F net, change in F net, and then the change in velocity, change position. And I found this model as it falls through. The time was a little bit off, so I went back and had the model print out what was the final position at each step, and then when it was around 165 meters or the height of the dam, I found the F net final to be around 141 newtons and the final velocity at that position to be 62.38 meters per second, which would be accounting for gravity and drag at that time frame. Since they were dropping the bowling ball onto a trampoline, I wanted to estimate the spring constant of said trampoline. I did scan through the video to find out what trampoline they were using. I found the model, and I found that the width of the trampoline was around 4 meters, and given in the data, the height of the trampoline was 2.7 meters. For this, I am going to use the return height of the bowling ball instead once it hits the trampoline, because I did see in the video that it bottomed out the trampoline, so I didn't want to take for the dissipation of loss of energy from it hitting the ground. So for this, I'm going to use the energy principle, including everything and leaving nothing in the surroundings. So putting the potential energy of gravity, potential energy of spring as the ball bounces back up in its return path once it bottomed out from the spring. I included the height of the trampoline to be 2.7 plus trackered in the continuous shot to be around 18 meters back up. So the spring constant should have been around 260 Newton meters. So conclusion, potential errors that most of the shots were not continuous and they didn't have like a clean falling shot, so it would have been difficult to estimate the total height. The bowling ball also bottomed out on the hit, so using the return height, it was a little more difficult to account for the total final return height. and we found the final velocity is similar to what it was calculated experimentally to be.